Have you ever felt completely lost trying to understand a complex coding problem? It can be overwhelming, right? If that's you, then you're in the right place. Today, we're diving into the intricacies of calculating the complexity of generating all permutations of a string. I totally get it. Trying to wrap your head around big O notation can feel like trying to solve a Rubik's Cube blindfolded. You're not alone in this struggle. Many people find themselves puzzled by these concepts. Here's the specific question we're addressing today. One user asked, how did the author arrive at the complexity of O of n squared times n factorial for generating all permutations of a string? If you've ever been confused by this, stick around as we break it down together. So what exactly is happening in this code? The function generates all permutations by recursively building strings. Each time a character is added, the remaining characters are permuted. This leads to a lot of combinations, which is where the complexity comes in. And don't go anywhere. At the end of this video, I have a special tip that will help you understand big O notation even better. To understand the complexity of generating all permutations of a string, we first need to recognize how many permutations exist for a string of length n. The user should note that the total number of permutations is n factorial, which is written as n exclamation mark. Next, let's consider how the algorithm generates these permutations. The user should observe that for each character in the string, the algorithm recursively generates permutations of the remaining characters. This means that for each character, we are making a recursive call. Now, the user should realize that in each recursive call, the algorithm processes a string that is one character shorter. This leads to a total of n recursive calls at the top level, n minus 1 at the next level, and so on, down to 1. As a result, the user can see that the total number of calls made by the algorithm is n factorial, multiplied by the number of characters processed at each level. This gives us a complexity of O n factorial for generating the permutations. Finally, the user should consider the additional work done at each level of recursion. Specifically, the algorithm constructs new strings by concatenating characters, which takes linear time. Therefore, the overall complexity becomes O n squared times n factorial, which is O n squared times n exclamation mark. Fun fact, did you know that the concept of permutations dates back to ancient times? Mathematicians have been fascinated by arrangements for centuries. Now, let's look at the answers provided by other users. This user provides an alternative explanation for the time complexity of generating all permutations of a string. They simplify the analysis by focusing on the recursive step of the function. They define the recurrence relation as Tn equals n times Tn minus 1, where n is the length of the string. Expanding this gives us n factorial, or n times n minus 1 times n minus 2, down to 1. They note that the base case, T0, involves printing the prefix, which is an on operation. This leads to a closed form of n times n factorial. Additionally, they highlight that creating the substring in each recursive call is also on, and since this occurs for n factorial calls, the overall complexity becomes n squared times n factorial. Let's take a look at another answer from another user. This user provides an alternative approach to understanding the complexity of generating all permutations of a string. They suggest calculating the complexity as the number of nodes multiplied by the computation at each node. They explain that the number of nodes can be expressed as the sum of factorials, leading to a total of n, multiplied by a series that approximates to n. This results in a complexity of O(n) tro n. Finally, they note that with real math, the series converges to approximately 1.7182 for n greater than 6, refining the complexity to O and n. That's all on that answer. Let's take a look at another one. This user explains the time complexity of generating all permutations of a string. They clarify that the complexity is derived from the number of times the for loop runs, which is represented as n times n factorial, or n times n exclamation mark. This is a simplification based on the estimated number of nodes in a graph representation of the permutations. They further elaborate that the maximum number of branches at each level of the graph is multiplied by the number of levels, leading to the upper bound of On times n factorial. Additionally, string concatenation within the loop contributes On, resulting in an overall complexity of On squared times n factorial. The user notes that the if statement's complexity is O1 since it only prints, and this is already accounted for in the loop's execution count. They also mention that if more lines were added outside the loop, those would need to be considered in the complexity calculation. Finally, they provide equations to determine the exact number of for-loop body invocations, emphasizing the need to account for the additional executions when the remaining string length is 0. Now, let's see a response from a different user. In this alternative approach, the user introduces a counting mechanism to track the number of steps taken during the permutation process. They note that by using a count variable, they consistently arrive at n factorial as the total number of steps. The user demonstrates this by modifying the original permutation function. They print the count each time a permutation is generated, illustrating how the count increases with each recursive call. Here's that special tip I promised. Practice breaking down algorithms into smaller parts. This will not only help you understand big O notation, but also improve your overall coding skills. And there you have it. Now you should have a clearer understanding of how to analyze the complexity of generating permutations. If you found this video helpful, don't forget to subscribe for more coding insights and tips.